So last week we were talking about block diagram operations, and I told you that by using either block operations or signal operations, you can find the transfer functions in a complicated block diagram more easily. So once you know what your inputs are and what your outputs are, then from that point on you can find individual transfer functions from each input to each output. And to do that, you need to assume everything else is zero. So, for example, here there are two inputs R and W with one input Y. To find the transfer function from this input to the output, you need to assume W is zero. Or to find the transfer function from here to here, you need to assume the other input is zero. So since there are two inputs and one input, for this case there are two transfer functions, and these transfer functions for G1 and G2. So that's how you can calculate. Today I would like to show you an example, and on this example I'm going to show you a closed loop control example. So far we talked about analysis, and in analysis what we do is, if we give a particular input to a system, how does that affect the output? Now we're going to see, to reach a particular output, what should the input be that we give to the system. So anyway, let me just okay, so this is the example cruise control problem. So it's a problem that you're all familiar with, I hope. So our system is a car. So probably we should use this figure instead. Okay, so this is our system. As the input to this system, we use the force we apply to the car by the engine, and obviously this force is controlled by the driver. And as the output, we use the speed of the car, which is represented by V. V as a function of t is the output of the system. And there may be a disturbance acting on this car, which is represented by F sub D. Okay, so this can be anything, so let's not worry about that at the moment. So if you want to write the equation of motion for this system, this is the mass which represents the car. This is the force we apply by the engine, using the engine, and this is the disturbance force. And we only model this force as the only additional force with these two forces is the viscous friction force. Okay, and as you know, viscous friction is a force that is proportional with the speed. Okay. So there's an additional force here which we can write as B times V. Okay, so that's the viscous friction force. We use a static engine model. In other words, the input force we apply to this car is the engine force. But instead of the engine force itself, what we consider as input is the gas pedal position, which is a more realistic assumption, right? So the driver has a gas pedal in front of him. So as he pushes on the gas pedal, that gas pedal creates the engine force. Okay? So we have an engine in between, and the input to the engine is the gas pedal position. This is so that should be explained somewhere here, but Okay, so here it is. I just didn't see that. Okay, so input is the gas pedal position shown by theta, which is normalized such that theta is equal to 0 corresponds to no gas, and theta is equal to 1 corresponds to full gas pedal deflection. Okay, so let's just write the equation for this system, which is this equation right there. But in fact, this is the equation, right? Mass times, or the total force should be equal to mass times acceleration, but I can write acceleration as the first time derivative of the velocity. Since velocity is my output, I use that as a variable in the equation. And I should write the total forces. So here I'm considering three forces, these three forces. The first one is the propulsive force, and the disturbance force is in the opposite direction, so I write the negative sign, and so is the viscous friction force, and that is B times V. So the differential equation for this system is the equation you see here. Let's see. So from here we can directly obtain the transfer function by taking the Laplace transformation with zero initial conditions. Okay, just the Laplace transformation of this equation is taken, and then this is the output. So these are the input forces. This is the control input force. This is the disturbance input force. Where the propulsive force is given by this engine model. So at this point I can draw the block diagram immediately, which is what is done next. So let me copy the So this is the car transfer function, which is this block. The input to that is the difference of these two forces, right? Propulsive force minus the disturbance force. So I use a summation junction to obtain this difference. The propulsive force comes to this junction with a positive sign. The disturbance force comes with a negative sign. And the propulsive force comes from the engine model, and the engine is another block here. The output of the engine block is the engine force, and the input to that is the gas pedal position. Okay, so this is the block diagram for this problem. Okay. Burada bir şeyiniz var mı arkadaşlar? Evet. Evet. So with this viscous friction, we actually model the friction force due to the road. Well, this is the friction that we model. Okay, so we model it as a damping force. So if the car goes faster, then there's a greater resistance acting on it, right? If you look at this model, this force is proportional with the speed. So obviously there are additional forces. For example, you can include aerodynamic drag force, but we know that drag force is proportional with the square of the speed, right? If you consider the aerodynamic drag force, for example, that is not included here. Well, the main reason is we cannot really use a square term in our equation, because if you try to include the aerodynamic drag force, that needs to be something like 1 over 2 rho v squared s times cd, right? So it needs to be proportional with this square of the speed. But this is a nonlinear term in our equations. So we don't want nonlinear terms. If you want to include something like that, you cannot obtain the transfer function. So to make the problem simple, we only use linear terms, and the best thing we can do at this point is to model this proportional with the speed. Okay, so in this block diagram there are two blocks. One block represents the dynamics of the car. The input to that is the force, and the output is the speed. And then we see a second block here, and this block represents the engine. Input to that is the gas pedal position, and the output is the engine force. But right now, for the engine, we use this model. So this is the equation we have for the engine, and this is the engine transfer function, right? So let me write an important note here. For linear static systems, transfer functions are constant numbers. For linear dynamic systems, they are rational functions of S. So for example, this is a dynamic system, and for that the transfer function is it's the first order transfer function, 1 over ms plus b, but for the engine we assume a static engine. So this is obviously not a very good assumption, because that means if you move the gas pedal, the engine immediately follows that without any delay. So if you look at this equation, if you, for example, give an input, if you step on the gas at some instant, this is, let's say, theta 0, kalem şu kenarlarda çok iyi yazmıyor. So if you step on the gas, the engine follows that, right? So this is Ke times theta 0. Kenarlarda yazmıyor deyip hala orada yazmaya şey yapıyorum ya. Bazen böyle problemin çözümü çok bariz oluyor ya. Öyle şeyler gerçekten fıkra gibi anlatılır ama işte adam gidiyor doktora, işte şöyle yapınca buram acıyor. O zaman yapma öyle diyor. Acıyorsun. Ben de kenarlarda yazmıyor deyip kenarda yazmaya çalışıyorum. So this is the input, right? So this is theta 0. And when you give a theta 0, the engine force directly follows that. So this is a static relation. But obviously in reality it's not like that. If you're driving a car, you always know that if you step on the gas pedal, it takes some time for the engine to reach its its performance, right? Or its so in reality you have something like this. If you step on the gas like that, the engine power will go something like that, and this duration obviously depends on what type of engine you have. But nevertheless, let's for the moment assume that we have a static engine. So this black is a static engine model, and red one is a dynamic engine model. So anyway, this is our block diagram. So there are two inputs. So let me draw my box on my block diagram. Well, this is inside the box, but I should make these arrows longer. So this in fact comes from outside the box. Okay, so there are two inputs entering my system. One is the gas pedal position. The other is this force Fd that I call. And then one output, which is the speed of the car. Now I can obtain two transfer functions. One from this disturbance force to the speed of the car, and another from the control input to the speed of the car. And these two transfer functions, let me just write it here directly. Neyse bunları da yazayım da tek tek. The first one is the gas pedal position, which is the control input. So to find the first one, the transfer function from the gas pedal position to the speed of the car, I assume this force is zero. And when I do that, this summation junction can be removed because there's nothing else coming into it. In that case, the output of the car is given by this times the input to it, but that I call G. G times what comes to that is the propulsive force, but propulsive force is given by Ke times theta, or theta times Ke. But since this is single input, single output system and linear system, the order of these terms does not matter. So G times K is the same thing as Ke times G. So the transfer function from theta to V is given by this multiplication, Ke times G. Okay? Find transfer function from Fd. I assume theta to be 0. In which case the output becomes equal to G times the input to that, but since in this case this signal is 0, input to that becomes minus Fd, right? I shouldn't forget that negative sign there. Is equal to G times minus Fd, or it's the same thing as minus G times, well, I should use capital letters since this needs to be a signal in S domain. So from here the transfer function from Fd to V is given by minus G. Okay? So if you want to write this system in matrix form, this is what you do. The output V is equal to okay. Okay, now let's study this problem a little bit. Okay, so let's assume that we apply some gas pedal to this car and see what happens to the speed of the car. Okay. First, let's see how the speed of the car changes if we apply gas pedal input. Bunun burada bir de biri varmış. Direkt burada 2'yi koymuşum ben. Okay, so the first problem is we apply a step input, which is a very reasonable input for this problem, right? We just step on the gas. So the gas pedal position changes according to this step function. And let's assume that there's some magnitude, right? So remember, this was normalized. 0 means no gas, 1 means maximum gas. And theta 0 has to be a number between 0 and 1. If you take the Laplace transform of the input function, that needs to be theta 0 times 1 over s, or theta 0 over s. And the speed of the car will then be given by, so this is theta 0 times 1 over s, and then ke times g is my transfer function. And ke is a constant number itself, but g is 1 over ms plus v. And I can write this as ke theta 0 divided by m 1 over s plus v over m. Okay, so to find the response here, we need to take the inverse Laplace transform. So let me just write you what you get in the end. If you take the inverse Laplace transform from here, you get the speed of the car as okay, so this is the solution to this. Well, I just skipped the steps here, but what I did is I took the inverse transform of this, and I first divided it into two parts by partial fraction expansion, and then I find the residues. In the end, I get 1 over s minus 1 over this thing. So the inverse of the first one is this, and the inverse of the second part is that, and in the end, this is the response I get. Okay? Okay, now let's take a look at the response in Matlab. Let me Okay, so this is the response I got. Well, before plotting the response in Matlab, I think it's a good example to think about how this function changes. So before going to Matlab, I think we should take a look at the problem from here for a while. Okay, so first I call this thing tau, and that allows me to write the output as follows: V of t is equal to doğru. Sen Tibet alması gerektiğini şuna bakarak mı söyledin? Yoksa genelde daha önce öyle görmüşlüğün var mıydı? Okay. Well, first, if we didn't have Matlab, and if you want to figure out how the speed of the car changes by looking at this function, first you can see the initial condition. Well, we expect that to be 0 already. But you can calculate it from here. If you put 0 here, the initial condition, the speed of the car becomes 1 e to power 0. But e to power 0 is 1, so this gives you 0. Okay? And then you can also calculate the final value of the speed, right? The final speed of the car we'll call it final. So as t goes to infinity from that exponential, I get 0 here, right? The value of this part becomes 0. So this final speed of the car is given by that part. Note that the same value can also be found by using what? Not final value theorem, right? And to apply the final value theorem, we need to go back to the function that was still in S domain. And apply the final value theorem here, you will see that you get the same value. Is it? Çok şuraya bir B geliyor sanki. Hep sen onlardan oldu. So that's good. This should be a B and not an M. So let me just fix that. Okay. Now it's good. Okay, so I know what happens at first. At first, the value is 0. And if I wait for sufficiently long time, the value should reach this, the speed of the car should reach this value. Okay, but I still don't know what happens in between yet. So let me just put it here. The speed of the car starts from here, and it reaches a value of this much. By the way, this should be theta 0, right? So there's no theta e here. So this is what I have, theta 0. So let me correct for that. Okay. Okay, the speed of the car is given by this expression, and this is the part that's equal to the final value of the car. So I just call that VSS. So this is the that function. And if I want to find out the speed of the car in the meantime between the final value and the initial value, I need to insert some time values here, right? So for example, if I, instead of t, the speed of the car at t is equal to tau is given by this particle e to power minus 1, and it's a constant number. 1 minus a constant number, is the value of that is 0.63. The speed of the car at t is equal to 2 tau becomes 0.86 VSS, because this 0.86 comes from 1 minus e to power minus 2. And similarly, the speed of the car at t is equal to 3 tau becomes 1 minus e to power minus 3, and this part becomes 0.95. And at 4 tau it's 0.98. In the end, the speed of the car changes like that. Or instead of drawing a new one, let me just go back to this one and okay. So let's give a short break and continue after the break.